Today, we are going to talk about blockchain. Blockchain is something much talked about these days. This concept became very popular after the emergence of Bitcoin, a cryptocurrency that is supported by this technology. Do you have any idea who created it, when it was created, and how it works? In this video, we will talk about everything you need to know. Blockchain was created in 1991 by Stuart Haber and Scott Stornetta. Everything started when Stornetta witnessed a manipulated biology research, where the results were altered with the use of a special ink. After that, Xerox, the company where they worked, told them that in the future all data would be digital. They knew this could be a big problem, as digital data is even easier to modify. This is what gave them the idea to solve the problem of changing data, and motivated them to create the blockchain, a system where nothing can be edited or deleted. This technology only became popular after the emergence of Bitcoin in 2008. It was named blockchain after Satoshi Nakamoto's Bitcoin white paper, where the words block and chain were heavily used. The purpose of a white paper is to advocate that a certain position is the best way to go, or that a certain solution is best for a particular problem. In the case of Bitcoin, the purpose would be to enable secure digital currency transactions without the need for a trusted middleman. The term blockchain was popularized as a single word only in 2016. Now you already know a little about the emergence of this technology. But how exactly does it work? As the name implies, it works like a chain of blocks, which contains information. Let's take a look inside a single block to understand it better. Let's talk about some of the fields that make up a single block of the chain. The first field we will talk about is the version field. It states the version that the particular block is using. Version 1.0, for example, is used for cryptocurrencies. Version 2.0 is used for smart contract, which will be the subject of a future video. The second will be the block size. It sets the size limit on the block so that only a specific amount of information can be written in it. The data depends on the type of blockchain. In the case of Bitcoin, it basically consists of three fields. They are sender, recipient, and amount in Bitcoins. Each transaction is hashed and stored inside the block. Now, you might be wondering, what does hashed mean? Understanding the hashing process is extremely important for understanding blockchain. So we will quickly explain this concept. Hashing is defined as the process of converting an input of any size into a fixed length string of text using a mathematical function. Initially, we have any entry, which can be, for example, 10 bitcoins from Fred to Jack. This input will pass through a hash function, and as an output we will have a hash. This is an example of a hashing algorithm. There are several different hashing algorithms. In the case of Bitcoin, SHA-256 is used. We should comment some important things about this hashing algorithm. First off, it's important to say that this is a one-way hash function. That is, it is impossible to get the original text from the hash. Also, it is important to say that the same input must always generate the same hash code. If the input is changed slightly, the generated hash will be very different. In blockchain, hash is used to represent the current state of a block and to ensure its immutability. A hash is commonly compared to a fingerprint. This is because it uniquely identifies a block in the chain and its contents. Okay, now that you understand this important concept, we can go back to our block. The next field will be the transaction counter. It's just a number that represents how many transactions are stored in the block. Merkle root is defined as the hash created using all transactions hashes inside the block. We also have timestamp. which is responsible for determining the exact moment when the block was mined and validated by the blockchain network. Non-C is the encrypted number that blockchain miners look for. Don't worry about this field, we'll talk more about it in a moment. Difficulty is a measure of how difficult it is to mine a block on a blockchain. We'll also explain this better soon. The hash or block header is a unique string that identifies the block and all its content. It is comprised of version number, previous block hash, Merkle root, timestamp of the block, difficulty target for the block, and the non-C. All these fields are used as input to generate the block header. Note that one of them is the hash of the previous block. It creates a link between the blocks in the chain. The hash of previous block, or previous header, as we just said, creates a link between the blocks. Hence comes the chain part of the blockchain. So let's now look at an example of a blockchain. As you can see, the previous hash of block 1 points to the hash of the previous block, just as the previous hash of block 2 points to the hash of block 1. You can see that the previous hash of the first block is 0. This is obviously because this is the first block in the chain. This one is called the Genesis block. So now imagine that we want to carry out a new transaction, for example, 10 bitcoins from Gabriel to Susan. This transaction will be converted into a hash, which will be stored within a block. Several other transactions will also be stored in this block. This block should point to the previous block and will have its block header. Note that at this point the transactions have not yet been completed. This is because the block has not yet been validated in the chain. For this to happen, the mining process must occur. The blockchain mining process, which in our example is Bitcoin mining, is a process in which a block is validated on the blockchain and its transactions are carried out. In the Bitcoin mining process, so-called Bitcoin miners look for a key called non-C. Non-C means number used only once. You may remember that non-C is one of the inputs to generate the hash of a block. When we were talking about hashing, we said that if the input is changed a little bit, the generated hash will be quite different. This means that if we change the non-C field, a completely different hash will be generated. In this process, miners are using powerful machines that solve complex cryptographic hash puzzles. Basically, they're guessing random values to non-C, trying to generate the correct hash. But what would be the correct hash? Let's take a look at this diagram, which contains all possible hashes. On Bitcoin network, there is a target, which is updated every 2 weeks. Anything above that target is rejected, and anything below is accepted. The target is often very low, which is why Bitcoin hashes often start with multiple zeros. This is what a real hash looks like. Once a valid hash is found, the block is added to the chain, and the one who found the hash will be rewarded in Bitcoins. There are still 2 important concepts related to this process that we must comment on. The first concept is difficulty. Like non-C, difficulty is also used to generate the block header. Difficulty is very related to target. It is defined as a numerical expression of how difficult it is to find a valid hash. For individuals, the difficulty value is more comfortable to interpret than the target. Basically, the lower the target is, the higher the difficulty, as it will be harder to find a valid hash. The second concept is proof of work. It is a mechanism that delays the creation of blocks. In Bitcoin, new blocks are created every 10 minutes. This makes blockchain technology more secure. Now we understand how the mining process works. When this entire process is completed, the block hash is changed by the new one found, the block is added to the chain, and its transactions are carried out. So now let's suppose that an attack takes place in block 1. The attacker changes the data and consequently its hash. This will make the previous hash of the next block invalid, as all other blocks will also be invalid. Just using hashes is not enough to keep the blockchain secure. Today's computers are very powerful, and it would be possible to rehash all the other blocks. Hence the importance of the concept we explained earlier, proof of work. Thanks to this mechanism, the process is slowed down. There is one more feature that makes blockchain secure. It is the fact that it is distributed. Blockchain uses distributed peer-to-peer network. It is a type of computer network architecture in which each participant is also a server and helps keep the system running. In normal applications, we have clients that connect to a server, while in the peer-to-peer scheme, all nodes are also servers. Anyone can join the peer-to-peer network. When someone joins the network, they receive a complete copy of the blockchain. Network users create consensus and validate blocks. They decide which blocks are valid and which are not. To tamper with a block in the chain, you would have to recalculate the proof of work for each block and control more than half of the peer-to-peer network. This is almost impossible to do. That's why blockchain is so secure. Throughout this video, we have given the example of Bitcoin. However, it is important to remember that blockchain is used for several other projects besides cryptocurrencies. Now we will give some examples of how blockchain has been applied and how it can be used in the future. Smart contracts. They are like regular contracts, except the contract rules are enforced in real time on a blockchain without ambiguity, eliminating the middleman and adding accountability for all parties involved in a way not possible with traditional agreements. This saves businesses time and money while ensuring compliance from everyone involved. Internet of Things. An increase in IoT products means more opportunities for hackers to steal your data or make you a victim of fraud or scams on everything from smart home devices to online passwords. IoT blockchain applications will add a higher level of security by preventing data breaches by utilizing transparency and virtual incorruptibility of the blockchain technology. Voting system. Voting blockchain applications could revolutionize electoral processes. Blockchain-based voting could improve civic engagement and reduce voter apathy by providing a level of security and incorruptibility that allows voting to be done on mobile devices. We won't spend too much time on this part anymore, so the video doesn't get too long. But we could also mention important blockchain applications for healthcare, media applications, gaming applications, automotive applications, personal identity security, and property and real estate. We'll leave a link in the description in case you want to read about all these possibilities. These are just some of the many possible applications for blockchain technology. If you are a developer, I recommend this site. The link will be in the description. This is a tutorial for a basic blockchain implementation. At the end of the site, there is a link to the GitHub repository, which contains the source code. Well, that's it for today. Thanks for watching, and see you in the next video.